Hi, my name is Brian Caffo, and this is the Multiple Variables lecture in the regression course on in our data science series. This lecture is co-taught by my co-instructors Jeff Leek and Roger Pang. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. What we're going to talk about in this lecture is the difficult topic of navigating when you have multiple predictors and choosing a model, and what are the consequences of including variables that you shouldn't, or not including variables that you should. Okay, so first point I'd make is we have an entire class on prediction and machine learning. So we're going to focus on modeling. So if all you care about is prediction, you have a different set of criteria. You have potentially different needs for interpretability and standards for generalizability. So it's just a different problem. So in modeling, our interest lies in parsimonious interpretable representations of the data. So we want a small model that's a good representation of the data that teaches us something in an interpretable way. So I like to think that there is no such thing as a correct model. And my friend Scott Ziegler, who's a renowned statistician, is often says that a model is a lens through which you look at your data, so that you can, the right model is whatever model connects the data to a true parsimonious statement about what you're studying. So a complicated model where you don't learn anything is less interesting than a parsimonious model where you learn something that's true. So there's so many ways that a model can be wrong. You can have the sampling assumptions wrong. You can have the distributional assumptions wrong. You can have the linearity wrong. You can have which covariates are included or excluded is wrong. There's a lot of ways. So we're just going to talk about, in this lecture, variable inclusion and exclusion. And then, I think something that comes up a lot in this class, good modeling decisions are context dependent. So, just as an example, a good model for prediction versus one for studying mechanisms to establish causal effects, those aren't the same thing. If you want predictions, you may be able to tolerate a lot more variables in your model than if you want to create kind of small parsimonious causal effects. So Donald Rumsfeld had this interesting quote, kind of infamous quote, I guess, and it goes like this. Donald Rumsfeld was is a former Secretary of Defense of the U.S., and he said, there are known knowns. These are things that we know. There are known unknowns. That is to say, there are things that we know we don't know. But there are also unknown unknowns. There are things that we don't know that we don't know. At any rate, it's kind of a funny quote that, or interesting quote that kind of gets talked about a lot in statistics because it relates very well to what we think about. So in our context, maybe known knowns are regressors that we know and have, and we should check whether or not they need to go into the model. Known unknowns are regressors that we'd like to include in the model, but we don't have. We either didn't collect or can't collect them. And then the unknown unknowns would be regressors that we don't even know about that we should have included in the model. Okay, so I like to call that the Rumsfeldian triplet. So some general rules about variable inclusion in regression models. So omitting variables tends to result in bias, unless the variables that you omit are uncorrelated with the variables that you're interested in are uncorrelated with the omitted ones. So this is why, in case you're wondering, we randomize treatments, or why randomized trials, randomized experiments are the standard for evidence, right? Because if you want to look at something, say a treatment effect, and you're worried you didn't include a variable, well, the randomization gives you some hope that the treatment assignment is uncorrelated with these unknown unknowns. Now, of course, if there's way too many unknown unknowns, then just by chance, they're going to be aliased with your treatment effect. which is a problem. And because they're unknown, you don't know how many there are. But randomization to date is probably the best strategy around for trying to balance unknown confounders. But often you can't randomize. So at any rate, so if you can't randomize and you really do need to include a variable in the model and you omit it, then it's going to induce bias in the variables, in the coefficients that you're interested in. So then you might say, okay, well, why don't I err on the side of caution and just throw everything into my regression model? So including variables that we shouldn't have increases standard errors. Any new variables, it turns out that including any new variables increases the standard errors of the regressors. And I want to emphasize this point. It increases the actual standard errors, not the estimated standard errors. So what happens with the estimated standard errors remains in question, because there's two parts to the standard error of a regressor. There's the part that depends on the residual variance, which you have to estimate, which residual variance has to go down if you include a regressor, even if it's unrelated to the response. And then there's the other part that involves the x's in the standard error. Any rate, what you can show is that the actual standard errors, not the estimated standard errors, have to go up if you add new variables. So you don't want to add unnecessary new variables.